So if we make a connection between masses and the gravitational field between those particles and our charges and the electric field between the charges, where this charge Q is in the electric field created by this charge, capital Q, similarly how the mass here is in the gravitational field created by this large mass there. So we have a particle times a field. And because in terms of the system, so, when we define the two masses as being a system, the work done by that gravitational field causes a negative change in the energy of that system. And I'm going to use the symbol U to represent the stored energy in the system. So the same sort of thing happens here if we consider the two charges a system. Then the work done by the electric field would be equal to the negative change in the stored energy of the electric field. So if the work done by the electric field is the force QE dotted with the displacement vector dr, we could write a small change in our energy as being like dUE is equal to the negative work done by the electric field, which would be equal to negative Q times the electric field dotted with dr. So integrating both sides here, so let's say we have a dUE is equal to negative QE dot dr vector. Integrate both sides, and we will get that the change in our electric energy, remember this integral of du would just give us U minus U initial, so that just gives us a change in the energy there, would be equal to negative, pull the Q out, integral of E dot dr. Now, just like the gravitational field causes a conservative force, meaning it does not matter what path is taken for an object that is at y equals 0, if it's going to go to some final position up here, it can take any path to get there, and the work done by the gravitational field will be the same no matter the path. So that's the definition of a conservative force. So the electric field is only doing work when it is parallel to that dr. So we describe this as being just the energy, the change in the internal energy of the two charge system. And we've talked about before how we could define the amount of electric energy per charge that is available for a charge at a particular position, and we call that the electric potential. So that was our electric potential, and this is where the word potential really belongs, and that's why we're going to say that this is the energy stored energy so that we don't get things confused. Now remember, energy is a scalar quantity. So when you take a scalar and you divide by, again, a scalar, then you get electric potential must also be a scalar. So if we're going to move between 2 points, let's say point A to point B in an electric field, there will be a change in electric potential energy. And if I look at it as a change in electric potential energy per charge, so let's take this charge and move it from point A to point B. So maybe the electric field is pointing in this direction here, and we're going to go from A to B along this path here. And so our charge, our little Q, will go from this point to this point, and there will be a change in then the electric potential changes. And if the electric energy, the energy stored, was equal to negative Q integral of E vector, electric field vector, dotted with the change in position vector, dr, and we're dividing by this Q here, then I need to divide by a Q over here, so divided by Q, and then that means that my electric potential difference, that's what I've got here because of the delta I have, would then be equal to the negative integral from point A to point B, as we're looking at this charge moving from one place to the other, of the electric field vector dotted with the change in position vector. And that's our electric potential difference. Now, a lot of times we set the initial electric potential to be 0 or some convenient value, just so that it is easy to calculate. So for example, a 9-volt battery means that the potential difference between the two poles of the battery is 9 joules per coulomb. So in a very simplistic way, we can look at electric fields, between 2 points. So here are some electric field lines here, and we can get a special case where we have a uniform electric field. And so from a positive plate to a negative plate over here, we get our electric field points from the positive side to the negative side, like always. And if you imagine moving a positive charge, this positive charge would experience a force, an electric force to the right. And so as it moves, the electric field would do positive work on the positive charge, and the electric potential energy of the charge would be decreasing. And if a negatively charged particle was introduced, and so maybe it's here, my negative charge, remember the negative charge would experience a force to the left. So that means that as it moves to the left, it is a positive work is being done on the negative charge as it moves to the left, and it's going to a lower energy state. So the change in electric potential energy would be negative for that charge there. So now if we were to force a positive charge from the negative plate over here to the positive plate there, if we were to force that positive charge to go here, then there would be a positive change in the electric potential energy of the system, and negative work done by the electric field force, and there must be some external force doing the pushing, because the electric field itself is only going to apply a force to take it to a lower energy state. So let's look at this uniform electric field a little bit closer. So our uniform electric field is nice because in this case, even if you had a particle and it moved from, let's say, here, a charged particle, and we applied a force to it so that it moved parallel to the plate or perpendicular to the field, and then parallel with the field. The only time work is being done by the electric field force is when the particle is moving parallel to the electric field. So just like in a gravitational field, when you carry a box across the floor and you're carrying the box and the height does not change as you're moving it along there, the work done by the gravitational force is zero and there's no change in gravitational energy. But then if you were to raise the box up perpendicular to the floor, raise the box up perpendicular to the floor, parallel to the gravitational field, you would be there would be a positive change in the gravitational energy. There would be negative work done by the gravitational field because the gravitational field is down while you're pushing it up. And there would be positive work done by the external force maker of the system, the person picking it up. So in so many ways, we're going to go back to mechanics to help us with understanding what's going on with our electric field. So the electric potential difference, that delta V, is equal to the negative integral of the electric field vector dotted with dr vector. And remember, a dot product by definition, the dot product is the magnitude of vector A times the magnitude of vector B times cosine of the angle between the two. And so in this case, there's no integral to be taken as the charge moves from this place down here, here to there. There's no integral to be taken because the particle is not moving parallel to the electric field at all. Here it is moving parallel to the electric field. Now I could have also taken this particle and moved it, in a diagonal direction there, and it would not matter still. The only change that matters is the change that is parallel to the electric field. Just like work done by a pulling force must be parallel to the distance, and the work done by the gravitational field, it only occurs when the object is moving parallel to the gravitational field. So then we'll have, if we look at our delta V, then would just be negative E dr, integral of negative E dr. And if we evaluate dr from like 0 to some distance d, so maybe we go from 0 over here to some distance d over here, then we can write our electric potential difference is equal to negative ED. Now let's talk about this negative sign here for a minute. The negative sign is important because it helps us to define where we have high electric potential. So high V versus low V. Okay, so if we have I'm going to redraw this because it's gotten kind of messy up there, but imagine we have this positive plate over here, we have a negative plate over here. Our electric field by definition is from positive to negative. Okay, so if our electric potential difference from A to B is negative, as we go from this side A to this over here B, then our electric potential at B will be lower than our electric potential at A. And this basically teaches us that electric field lines run from high electric potential to low electric potential. Now, if we consider this relationship here for our electric potential difference and the D, now if D is the distance from A to B, if we move B anywhere inside between these two plates here, maybe I put B at this point right here, or maybe I put B at that point there, or down here, or down here. No matter what, the distance that is parallel to the electric field is the same all along this line, and it would be the same all along this line, and it would be the same all along this line, and even you can add some here in the middle. It would all be the same along here. So all of these are equipotential lines. So equipotential lines. So that means that even if you have a charge that goes from this point here to this point there, the electric potential difference is the same if it travels in this path to get there, or if it travels in this path to get to that spot, or if it travels in a straight line to get to that point, straight line, or even a straight line to get here. The electric potential difference of all of these places here is the same no matter the distance, because the electric force is a conservative force, like the gravitational force. So if our electric potential difference can be described as the negative E electric field dotted with the dr, then I could write this if I'm talking about a little change in this electric potential. Remember, the delta just means a change in, or a little d. V would be equal to negative E electric field dotted with our position vector. Now, if I want to find the electric field, if the electric field is parallel to the little dr displacement, remember that little dr displacement there, then this would be dv is equal to negative E dr, and then I could write the electric field as being the negative derivative of the electric potential with respect to r. Now I've used that r to mean any change in position, X, Y, Z, it doesn't really matter. So let's say, because of the direction I've drawn up here, that this isn't just dr, but this right here is a dx. So then I would have that the electric field in the x direction would be equal to the negative derivative of the electric potential function with respect to x. And so I would have the x component of the electric field, and that works really well if you have something like I've drawn several times here, where you have two plates separated, positive, negative, and those two plates have an electric field from positive to negative directed uniformly between the two plates. So other distributions may look like a spherical sort of distribution. So meaning, what if we just have a positive charge, positively charged object? Then the equipotential lines would be around here. Remember, equipotentials show where the potential difference will be the same, and because it is a 1 over r square value, we have to get further and further away for there to be equipotential. And electric field lines run from positive to negative or perpendicular to those equipotential lines. So in this case, the spherical symmetry allows us to determine the electric field strength as being negative dV, and in this case the dr is representing a radial component. So if we are looking at positions like this right here, our dr is a little bit of the radius there. Now if we have some arrangement of charge where maybe you have a dipole where you've got a positively charged object over here and a negatively charged object over here, and we know from experience that electric field lines will run from positive to negative, from positive to negative, from positive to negative, and our equipotential lines will cut through perpendicular. So all of these are our equipotentials, and what's important to note is that there's not a uniform function here, and that it is dependent on x, y, and z. And so we could then write our electric field in the x direction would have to be the derivative of the electric potential with respect to the change in position x. The electric field component, maybe in the y direction, would be negative of the derivative of the electric potential function with respect to y. Electric field could have a z component, which would be negative dv dz, to find the component of the electric field in the z direction. So in general, we can think of this as being a partial derivative. So the electric field function with respect to r meaning that it could have x, y, and z directions, is equal to the negative partial derivative of the electric potential function with respect to r. So taking the partial derivative, and so all of these functions here are actually what we call partial derivatives So we are taking the derivative of a potential function with respect to each one of the dimensions individually. So as you take the derivative of the electric potential function and you are taking the partial derivative with respect to x, then you're going to treat all other variables as constant and only derive in terms of x. This allows us to take a scalar value. So remember, this electric potential is a scalar, has no direction. And by taking the partial derivative, we're able to find a vector value. So we're able to determine the vector from taking this partial derivative of a scalar. For simplicity's sake, we often write this as the electric field is equal to the negative gradient of the electric potential function.